We will be looking at problem number 6.64 on page 378. It deals with testing for HIV, the virus that causes AIDS. The test is called the Eia Test. It gives us some data there, and it says suppose that 1% of a large population carries antibodies to HIV in their blood. A says draw a tree diagram for selecting a person from this population and for testing his or her blood. This is one of my favorite problems in the book, and it really is going to eliminate some interesting ideas with regards to probabilities. So we'll begin by drawing a tree diagram. In order to draw this diagram well, we'll need to define some variables in this problem. I'm going to say that plus will equal a positive test. That is, you took the Eia test and it came back positive. Negative will be a negative test. Okay. Also, I will define H to be you have HIV. And H prime will be not having HIV. That is, we can certainly have the virus and then have a negative test result. We'd call that a false negative. We can certainly not have the virus and come back with a positive result, a false positive. Or we can have the test desired result, that is having the virus and coming back positive, or not having the virus and coming back negative. So we are given that in some population 1% of the people will have HIV, therefore the complement will not have it, 99%. Note that in our tree diagram here, that at each split it'll sum to 100%. Okay, the table tells us that if antibodies are present, that 0.9985% will return a positive test. Positive test will be 0.9985. That is 9,985 people out of 10,000 who have HIV will test positive on this test. So the negative result will be the complement of that. 1 minus that is 0.0015, and we see that number on the chart as well. Well, for the portion that actually does not have the virus, that is. Again, we see this phenomenon where it sums to 1 at the split. If you do not have HIV, you will test positive. That is a false positive result in 0.006. That is 6 out of 1,000 people without HIV will test positive. And a negative result will occur in the complement, 0.994. Alright, so these are the facts as presented in the problem. It looks like the test is very accurate. If you have the virus, if you do not have HIV, 0.994, that proportion, you will return a negative test. 99.4% of the time it will return negative. If you do have the virus, even more accurate, 99.85% of the time. 9,985 times out of 10,000 it will say such. So the test appears remarkably accurate. Alright, that was part A. Part B says, what is the probability that the Eia is positive for a randomly chosen person? We want the probability that the test will return positive. Well, this group here and this group here our positive results. To find what proportion those are, we need to do this product. We need to find the probability that you are HIV, that you have HIV and you return the positive test. That's this result here. The probability that you have HIV and your test is positive. Well, that's simply the product of those two. This is equal 0.009985. It is simply the product of 0.01 and 0.9985. All right. Well, the positive results will also be these people. That is, they did not have HIV, but they tested positive. So this is the probability of not HIV and our positive test. This is 0.00594. 0.00594. All right. So these two proportions are all of our positive results. So the probability of a positive result will equal the sum of those two. 0.009985 plus 0.00594. That is equal 0.015925. So we saw earlier that 1% of the population does have the virus, but 1.6% roughly is going to return a positive test. So that seems a little discouraging. All right. Next part. C. What is the probability that a person has the antibody given that the test is positive? So, has the antibody given that it's positive? Let's see if we can come up with our notation. Probability that we have the antibody, we have HIV, given we have a positive result. Well, first let's define this notation using our formula chart. The formula chart says that the given part's the denominator. Alright, so we want the probability of a positive result is going to be in the denominator. Well, that's that previous sum. The numerator is the intersection of those two. So it's the probability of HIV and positive. Okay, well, that was our result here. These are the people that actually have HIV and they've tested positive. So this is just a simple division. The probability of a positive is our previous 0.015925. The probability of HIV and positive is 0.00995, which we see is remarkably close to the 0.01% of the population that is HIV positive. So 0.009985 divide 0.015925. That is 0.627. Check my arithmetic in this, but I believe that that's close. That's approximately 63%. So approximately 63%. Alright, so what we see is, given that you return the positive result, there's only a 63% chance that you actually have the virus. Startlingly enough, 37% of the people that come back with a positive result don't have the virus. So that's a little bit scary to think about, even though the test is so accurate, because most of the population does not have the virus, of course we're going to get many false positives. The frequency of not having the virus to having the virus is 99 to 1. So almost everybody taking the test doesn't have the virus. That's why we get such a large proportion in this situation here relative to this one, because of the amount of the population that does not. And if you think about these results for a little while, you'll probably come up with some more interesting conclusions.